Okay, so today we are going to discuss this paper by Geoffrey Hinton, which is actually known as the Forward Algorithm, some preliminary investigations. And right now it is 2021. This paper was actually published in 2021 and it's 2025 this time. So already 4 years have passed since this paper has been published, and a lot of interesting work has happened since then. But the reason that I am covering this paper is because it has a lot of fundamental stuff which most of the people on the internet seem to be missing. And what I am going to basically do is go through each line of the paper and try to explain what forward is about and how actually like Hinton might have invented it, so that you don't understand it from the perspective of like, okay, this is how it works and just the algorithm, but you try to understand the intuition about like what is actually happening. Okay, so let's go through the abstract. So what it says is that the aim of this paper is to introduce a new learning procedure for neural networks and to demonstrate that it works well enough on a few small problems to be worth further investigation. So this is not like something which is gonna surpass like which is not like a new, it is a new learning algorithm, and it still hasn't been proven to work well in practice, but that's why he says that this algorithm is preliminary of sorts. uh, okay, so now let's go through the other part. So he says that the forward algorithm replaces the forward and backward pass of the backpropagation with two forward passes, one with positive data and one with negative data. So in a standard neural net, when you are doing backpropagation, you feed your input here and then it goes through the network, and that's called the forward propagation step, and then you compute the loss and then you gradually come back, right? So you come back in this iteration, and this is like the second pass, which is like the back propagation. So what he's saying is that instead of in back propagation there is one forward pass and one backward pass. Instead, in forward algorithm, what happens is that you have a neural network in which what happens is that you you have like some data, and you are doing two passes through the network in order to do the learning, and somehow it works. And let's try to understand like how it works. Okay, so this whole part is like the abstract, and that's not really important. So let's just first try to understand like what is the core intuition and how this algorithm works. Okay, so the first part he wrote was actually titled "What is Wrong with Backpropagation?" And what he's saying is that backpropagation remains implausible despite considerable efforts to invent ways in which it could be implemented by real neurons. So the point is that it is not clear in the brain how backpropagation happens, and there are several reasons for it. So the first reason is that there is no evidence that the brain explicitly propagates the error derivatives. So in the case of like in case of like neural networks, like what happens is that in the brain like the connections are like this. So when you are doing backpropagation, generally what happens is that you have to backpropagate the gradients via chain rule, and that is actually what we have not seen in the neural networks, that there is no such explicit mechanism for information passing which is happening. Rather, all the connections are local. So for example, this neuron is only connected to this neuron, and this neuron is only connected to this neuron and this neuron, right? So this neuron can only exchange message with the neighboring neurons, and that is a property in the brain, and that is what the backpropagation is not respecting. And similarly, the other things that Hinton writes is that the top-down connections from one cortical area to an area that is earlier in the visual pathway do not mirror the bottom-up connections at would be expected if backpropagation was being used in the visual systems. So basically, the key point is that let's say that you have so what happens is that in a brain, what happens is that generally there are some bottom up connections like this. So if you have layer 1, layer 2, layer 3, so there are certain connections like this, and then there are certain connections which go back. So these type of connections are known as feedback connections, and they are really important. And these connections are also known as the top down connections. Okay, So now the key point is that in the brain there are a lot of these top-down connections and also bottom-up. But in most of the neural networks, what you will see is that there is no connection which comes from higher layer back to the lower layer. So we are not able to model it in some way. Now, there are two reasons why we are not able to model it. So, the point is that if you see here, this graph is forming a cycle. So, if you were like computing a loss here, it would not be clear how to like update this neuron and this neuron, all these three neurons together, because it is forming a graph. So, since it is forming a graph, we don't know like which node to update first, right? Because if we update this node to know this node, it needs to know the value of this node, and that's not possible, right? So since this is like forming a sort of cycle, it is very difficult to update the neural network in that way. Okay, so now the other part is that the okay, so that is what like Hinton is basically saying here, that we have a lot of top-down connections which form cycles, and that's why like learning can't proceed in a normal neural network. Okay, so let's move further. So this is all that is wrong with backpropagation. And then the other thing which Hinton says is that the problem with backpropagation is that it requires perfect knowledge of the computation performed in the forward pass in order to compute the correct derivatives. So basically the key point is that let's say that you have like a function f, and you know that this function is x square, right? So your y is equal to x square, and the only way like you can perform a backward pass here is if you know the gradient of y is basically 2 times gradient of x, right? So if you know this, only then you can perform the backward pass. So for backward pass, like if you have like several of these layers, you need to know the perfect mathematical formulation of each of these layers, and only then you can train your neural network. So for each of the layers, it is necessary to know like what is its mathematical function, and it's also important to know what is like the what is like the what is like the expression to compute the gradient, right? So what's the mathematical expression to compute the gradient? And the reason like it does not make sense from a neuroscience perspective is because in the brain what happens is that the structure of the layers themselves is changing as we are doing the learning process. So since the structure is changing, it is very difficult to actually make it work, right? So there is no learning algorithm which will allow the structure of this each of these layer to change and then still be able to train it. Because in backpropagation, you first assume that during the training, the structure of the neural network is fixed. Yeah, so in backpropagation, you first assume that the structure of the neural network is fixed, and then you train it, right? So that's the problem. So in a normal neural network, you first have to take the neural network, define its structure, and then you train the weights. But in the brain, what happens is that the structure is also changing along with the weights, also changing. And that is a property which in neuroscience, like a lot of us people call as plasticity. And that is something which is like a big disadvantage of backpropagation, and it's not able to do that. Okay. Now, the other part here, what Hinton says is that reinforcement learning scales badly and cannot compete with backpropagation for large network containing many millions or billions of parameters. So, what he's saying here is that there's a reason that backpropagation is able to work so well. So, let's say that we have like four neurons connected to all of them. So now we want to know like so let's say that we have like a list of neurons which are connected, and we want to know like how much change each weight, like how much each weight has to be changed in order to give like the final output loss, right? And the problem is that if you change the weight too much, your loss will go up. So you want to know how to change the weight on each connection in order for learning to work well. So now let's say that you have four neurons here and three neurons here. So you have basically 12 neurons. So you have 12 connections. So you have 12 weights. So at a particular time, what you can do is that you can actually keep like 11 of these weights constant, and then you can fluctuate just one of the connection, right? So you can just fluctuate like one of the connection, and you can see whether the loss goes up or down. And if the loss, and then that will allow you to compute the gradient, right? The gradient, like what happens if you change that weight somewhat. So now the point is that you have to do this process for you have to do this process 12 times, where each of the times you're keeping like one of the weights as all the weights as constant and only changing one of the weights. And that's the problem with reinforcement learning. So in reinforcement learning, what you do is that you actually uh, you actually fix all the variables and then only change one variable, right? So but in backpropagation, what happens is that you can compute these gradients in a single backward pass. The reason is that when you are so you don't have to like do this 11 these 12 steps anymore. And that is why Hinton believes that reinforcement learning can never offer a good alternative to backpropagation. Because in reinforcement learning, if your network contains 1,000 parameters, then you will have to hold all the parameters constant except one, and you will have to repeat this process for all the possible inputs. Okay, so now this is good. And so we can see that there is like several problems in backpropagation which is happening. And then another thing like which he writes is that the forward algorithm is somewhat slower than backpropagation, and it does not generalize as well for backpropagation. It does not generalize as well, and it is unlikely that it will replace backpropagation for applications where power is not an issue. So the point is that even though like he invented this new algorithm, it is not clear, like it is not gonna mess up with backpropagation, and backpropagation will still remain in like the workhorse. But what the future will look like is basically something as follows. So we will have like a big server, and this big server will have some models which are trained with backpropagation. And then we will have a small server, and then the models which are on this server will be trained actually will be actually the copies of this big model which were like trained with backpropagation. But then the point is that the models on the edge devices can actually learn during the inference time, or they can also learn during like these models can also learn on the edge devices. And since there is like very less memory, as in there's very less memory on edge devices, you can train these models by forward type of algorithms, because it will intrinsically occupy very less amount of memory as compared to backpropagation. So that is like the key selling point, why forward type of model is going to help in learning the models on edge devices, because it does not consume as much memory as backpropagation. And why does it not consume that? Let's discuss that. So basically the key point is, let's try to understand like what the forward algorithm might be about. So let's say that you have like a neural network with 5 layers. Okay, so now the point is that if you have to like optimize your neural network via backpropagation, you have to store like several things. So for every input, like your so let's say that each of these matrices, the weight matrices in each of these layers is these 5 matrices. And then when you send it the input, so for every layer you have to compute its, so you are storing like the weights, you're storing like all the weights of all the layers in memory. And similarly, what you're doing is that for all the layers, when you're making the forward pass, you're actually computing the activations, right? Which is W1x, W2, W1x, and then W3, W2, W1x. So you're computing the activations of each of the layers and you're storing them. So you're also computing the activations, you are storing the weights. And also what you're storing is you are also computing the gradients, so how much each weight has to be changed. So you are computing the gradients, so you are gonna have like some gradients for layer 5 and then some gradients for layer 4. So you will also be storing the gradients. And since the number of weights in your network, the number of gradients is same as number of the weights, so essentially you are consuming twice the memory, one for holding the weights and one for holding the gradients. And so as you can see, like it is actually holding, so you have to hold all of these three things in memory, and that is what makes back propagation very bad, because you're storing like three things, um, and this is not required. So the key memory cost is actually coming from these two parts, which is that you have to store the activations and gradients of all the layers in the memory, which makes it like very inefficient in practice. So then the next question becomes is basically we have to invent a new learning algorithm which can actually help us in a better way to like do learning, and which can help us in like uh, getting out of this memory cost. So how do we do that? Okay, so the idea is something which Hinton calls as piping the data, and what it goes as follows is that like this. So let's say you have like these five layers. So now you want to invent a learning algorithm in this way that whenever you feed your data here, as soon as any of the layers sees that data, it updates itself, and it never stores the gradient. Okay, so when the input comes to layer 1, what it will do is it will somehow calculate gradients, and it will update its own weights. So it will update like the weights in that layer, and then once it has updated the weights, it can essentially get rid of the gradients, and it doesn't need to like store these gradients anymore because it has updated its own weights. And then what it can do is that it can pass on the resultant activation to the second layer, and similarly the second layer, as soon as it receives data, it can update itself, and then it gets rid of the gradients, and then it passes the data further. So basically whenever a particular layer is receiving the data, it is updating on the fly, and the layer before it has already deleted its own gradients and its own activations. So at any particular instant, the only thing which you are storing is basically the activation of the current layer and the way and the gradients of that layer, and then you can essentially get rid of the gradients once you have updated that layer. So the one line takeaway is that your network consists of several layers, and once you pipe the data in, as soon as you give the data as input, it goes through several layers, and then whenever any layer receives the data, it updates itself. So it is able to somehow understand how much the weights in that layer needs to be updated, and it updates that, and then it deletes its own gradients and it passes on to the layer next to it. And in this way, like all the layers update as soon as they are receiving the data, so there is no locking issue which is happening. And what do I mean by locking issue is something as follows. So let me clear this. Okay, so uh, what I mean by locking issue is, okay, so okay, so let's say that you have a neural network with five layers, and you are trying to do back propagation on that. So this is layer 1, layer 2, layer 3, layer 4, layer 5. So when you send your data as input, what will happen is that you will have time step 1 when it passes through layer 1, time step 2, time step 3, time step 4, time step 5, and then the data will come back 6, 7, 8, 9, 10. So if you see at the layer 1 will receive the gradients back at time step 10. So the layer 1 received the data at time step 1, but it received the gradients at time step 10. So it was only able to update itself at 10th time step, and between the time step of 2 to 9, 2 to 10, it was not doing anything. So for 8 minutes, for 8 seconds, it was just waiting for the layers after it to finish the computation. And this is the problem which people call as locking problem in backpropagation. So since it was like locked, that's why this layer was left waiting, and since it was left waiting, it was actually not doing any useful compute on the machine. So so this locking problem is a core problem in backpropagation, and you can assume that if the network is like very deep, For example, if there are like 1,000 layers after the layer 1, then the problem will worsen because you have to make 1,000 passes and then 1,000 backward passes, and it will give you like 2,000 time steps, and the first layer is like starving for the gradients to come back, so that is like 2,000 time steps, which is a very bad, which is like inefficient way to update the neural network. Okay, so this is like a this is like a problem in back propagation, and the way like Hinton, the way like the forward solves it is basically using that sort of logic, right? Okay, so now we are left with two things. So we are left with two things. One thing is that we want to define a way in which when you're piping your data through the neural network, whenever you are piping your data through the neural network, you need to come up with a way so that the neural network is able, each layer of the neural network is able to somehow find the gradients it needs to update itself as soon as it receives the input data. And how does it get that gradient? Because it cannot rely on some global loss function to optimize, because then that will lead to the locking issue which I talked about earlier. Okay, so there are two ways like you can, so if it cannot do that, there are two ways. Okay, so the point is, here what Hinton does is that he introduces this notion of positive data and then another notion of negative data. So what is a positive data and what is a negative data? So let's have a look at this. So let's say you have a digit which is like a digit 7. So this is a digit of 7, right? So now what you can do is that on top left you can define like 10 pixels, which is like corresponding, so this digit can belong to like all the 10 classes, which is like 0, 1, 2 and so on till 10. And now if any of these classes is set, so you can imagine that the sum of this, the sum of values at these pixels is basically telling us the probability of this particular image belonging to class 7. So if you set like a pixel of 1 here, what it means is that and set all of these values as 0, what it means is that this image of 7, we are telling the network that it actually belongs to class 0. So this, so if this image actually, if you are actually telling it that this if you're telling the network that the 7 image belongs to the class 0 by setting that pixel as 1, so this is a bad sample. This is a bad sample because you told the network this is actually belonging to class 1, whereas it actually belongs to class 7. So if you set the pixel corresponding to class 0 as 1, then that means that it is a bad sample. Okay, and when will it be a good sample? So the neural network will think that it's a good sample if you set the pixel corresponding to class 7 as 1 and all the other pixels as 0. So now this is a good sample. So now the idea is that you will have this input image, which is like the class which you're trying to classify. And what you will do is that you will try to input like the labels in it. You will try to give it like the input data in such a way that if the class indicator, like if you tell it like if it belongs to the correct class, then it's a correct good sample, otherwise it is a bad sample. Okay, so now that we have established the notion of what is a good sample and what is a bad sample, we will talk about like how do you actually optimize this. So you can imagine that you have this type of neural network, and what you will do is that you will have these two images. One is belonging to a bad sample and one is a good sample. So now what you want is that whenever you are piping like your data through such a network, what you want is that it should activate like it should activate a lot high for positive sample, and it should activate very low for a bad sample. So let us look at what he says here. So let's look at this equation. What this equation means is that, for example, let's say that your layer, let's say you are optimizing the fifth layer, and you, that layer has j number of neurons. So let's say that layer has j number of neurons, and when you send your data as input, it outputs like the representation y1, y2, y3. So basically, you are outputting like a lot of activations in this layer corresponding to each neuron in this layer. So what you want is that if you take like the sum of like the squares of these activities, it should be pretty high if it is like a positive sample, and it should be pretty low if it is a negative sample. So if that's what this equation is essentially doing. So what you do is like you're summing over all the positive responses of the neurons in this layer, and then you're subtracting it from theta, and you're passing it through a sigmoidal unit. So what it means is that if your responses are greater than theta, then it means that the sample belongs to a positive class. So you will maximize the goodness in this case. And if your response is less than theta, you will actually minimize the response here. So this is what the fundamental algorithm of our forward is. And now the key point is, so this is what he did. Okay, so let me show you some other figure. Sorry. Okay, so what you can see here is like some of the samples which he used. So for example, here, like here what he's showing is that these are like the samples which belong to like different classes. So this is like one of the samples which we are talking about. uh, Let us also look at like another example here. So now the key point is that you have this positive data and you have this negative data, and you are trying to pass it through the network, and whenever it sees positive data, it outputs a high response, and whenever it sees a negative data, it passes a low response. Okay, so now we understood like what is a positive data. So if you have like a number 7, which is a particular digit, if you have the correct pixel of class 7 and you set it as 1, that's a positive sample. Now let's have a look at what is a negative sample. So negative sample, you can construct a negative sample in two ways. Okay, so let's talk about like a digit 7. Okay, and let's say that it can belong to class 1 to class 10. So here there are 10 possible classes, and then for 7th class it can belong to a ground truth class. But for the remaining 9 classes, if you set any of the pixel as 1, then the network essentially will that will become like a bad sample, right? So let's say that you created a negative sample in this way, in which like you set like all the pixels except the ground truth, any of the other pixels you set as 1, and it's a negative sample. So basically what you are telling the network is that, hey, the so in the top left border of the image, only one pixel can vary, and sometimes it can be positive and sometimes it can be negative. So that is actually a very bad problem, right? Because your network doesn't have the ability to just distinguish between the pixels, just one pixel. So let me give you a more further example of this. So let's say that you have 7, and here for class corresponding to ground truth class 7, you set that pixel as 1, and for class corresponding to pixel 0, you set that as 1. Okay, so now in this case what will happen is that in both of these cases the figure is essentially the same. The pixels of the image are essentially the same, except just one pixel except just one pixel for these classes corresponding to class 7 and class 0. So it is like very confusing for the network to just distinguish between these two images on the basis of just one difference in the pixel, to classify it either as a positive sample or as a negative sample. And that is why you cannot construct negative samples by just taking like the samples and merely setting like some of the samples of non ground truth classes as ones, because the network has this symmetry problem when it's not able to distinguish between just one pixel. Okay, so that is like the key point which Hinton is talking about, and that's why what he talks about is a way to generate like the negative samples which are used during the learning process. Okay, so how does he create negative samples? So the way he creates negative samples is basically that, um, so let's say that you are actually, let's say that you have an image of class 5 and you want to generate the image, you want to generate negative samples corresponding to class 5. So now what will happen is that since you want to generate like negative samples corresponding to class 5, what you will do is that you will pick any other classes other than 5. So in this case, he picks class 7 and class 6. And then what he does is that he basically masks them out. So he takes like the alpha amount of this class and 1 minus alpha times of this class, and he merges these two digits, and then finally what he ends up is this hybrid which he calls as negative data. So this is the negative data for the class 5. So you can imagine that you can construct this negative data, and the algorithm for that is pretty simple. So first you pick like the ground truth class which you are concerned with, and then you pick like two other classes which are not the part of ground truth class, and you sample their digits, and you take alpha times of class 1 plus 1 minus alpha times class 2. So this is like a new image which you obtain, and this is the one which is actually acting as a negative data for your network. Okay, so this is good, and this is how you create like the negative data. So the algorithm is pretty simple. You have this neural network which you are trying to optimize, and what will happen is that you pass it your data x. So it can say it's positive data, negative data. For positive you want every layer to output high response, and for negative data you want every layer to output a low response. So that's the whole idea, and you can construct like this negative data. You can construct this negative data as a mixture of two classes which are not belonging to the ground truth class which you are considering. Okay, so this is like the fundamental idea behind forward. And now actually let us look at what Hinton wrote, so that we can satisfy ourselves that what we have discussed is actually what Hinton actually told. Okay, so here what uh, he said that the idea is to replace the forward and backward passes of backpropagation by two forward passes that operate in exactly the same way as each other. So there is one pass in which you have a positive pass, and you adjust the weights to increase the goodness in every hidden layer. Goodness here just refers to the fact that when your network is processing like positive data, the sum of square activities for each neuron in that should be positive. Okay, so that is what goodness is. And similarly for negative data, it should decrease the goodness, so the sum of square activities should be low. So that is what like he's saying. And then we already talked about the equation which he talks. So one thing which I really noticed well about Hinton here is that if you look here, okay, yeah, we will talk about in the next thing. So now one thing he talks about is learning multiple layer of representation with a simple layer wise goodness function. So what he says is that if the activities of the first hidden layer are used as input to the second hidden layer, it is trivial to distinguish positive from negative data by simply using the length of the activity vector in the first hidden layer. Okay, so what he is saying is that let's say you have two layers. Okay, let's say that you have these two layers, and your network is trying to learn like good features between them. Okay, so now as soon as this network will see like some this layer L1 and L2, as soon as layer L1 will see like a positive data, it will output a vector which is very high. Okay, and for negative data it will output a vector which is very low. Okay, so now the key point is that the vector will be very low, so its magnitude is going to be very low, and similarly the vector is going to be very high, the magnitude is very high if it sees a positive data. So what the so the second layer, the job of the second layer becomes far easy, right? Because if it looks at these two vectors, one has a very high magnitude and one has a very low magnitude, then it can easily fit like its parameters to distinguish between like this positive data and this negative data. And that is something which we don't want, because then in that case, if you give it like some very large number like like 100, and then some very small number, point 0.1, point 0.2, it is very easy to like distinguish between these two set of numbers. One is very large and one is very small. So the way like, so if you do that, like whatever features you end up learning will actually not be very good. And that's why what Hinton says is that he wants to apply layer normalization between the different layers in forward. So what happens is that if you have layer 1 and if you have layer 2, and if you apply layer normalization in between, so what will happen is that if you have two vectors, so let's say you have one vector which is very large and you have one vector which is very small, and once you normalize them, all of these vectors will actually start to lie on a hypersphere. So their lengths will be different. So their lengths will be different. So their lengths will be 1 and their angles will remain same. Okay, so their lengths will come to 1 and their angles will remain the same. Okay, and because the magnitude is now constant, the neural network again has to distinguish between these vectors, which vector belongs to the positive sample and which vector belongs to the negative sample. And since the length is identical, this job is like very difficult. Okay, so that's the whole idea here, that as you're proceeding from one layer to another, you want to destroy the information via layer normalization, so that what you end up with is equal normalized vectors, and you have to distinguish still again which is a positive sample and which is a negative sample. And that's a task which is really hard for every layer of the neural network in this way. Okay, so that is one line takeaway from here, is that he wants to apply layer normalization between different layers of the neural network. Okay, this is good. And like you might think like it's trivial, right? Just apply the layer norm and it's very easy. But the key point is that there was a time when people were not able to even understand how layer norm is working, right? And it was not clear. Okay, let me share my screen again. Okay, okay, so now that this is clear, let me open this up. Okay, okay, so now we are back to what we were talking about. And uh, okay, so that is good. uh, okay, so now let's talk about like how a forward type of network will be actually trained, right? Because you can't do any back propagation. So there are two ways to do there are two ways. So we have talked about how the training works when you're trying to increase like the square you're trying to increase like the squared cost of like the layer norm, the layer activities if it's a positive data, and you're trying to decrease it if it's a negative data. Now let's talk about how does inference look like. How does inference look like? Okay, so how does inference look like in forward is that, let's say that you have a neural network. Okay, and let's say it has these 5 layers again. Sometimes you're passing it positive data, sometimes you're passing it negative data, and you want to actually know you want to know how to do inference on top of it. Okay, so let's say that you pass the data, and then after you pass it, basically you have two options, right? So you have learned this part of the network with forward propagation, with forward algorithm, and then on top of your last layer, what you can do is you can train a softmax. You can train a softmax to actually take the features from the last layer and then predict like which class it belongs to, right? And then that should be easily possible, right? So the point is that you can imagine that your network is partitioned into two parts. One is this 5 layer net, which is trained via forward propagation, and like the layer gradients of one layer are never passed to the gradients of the previous layer, so there is no back propagation involved. And this softmax is nothing but it's like just a bunch of linear layers with a with a softmax function, right? So you can train like just one linear layer through the loss, and you can update these weights, and then you don't need to send this back to the remaining 5 layers of the network. Okay, so you can imagine that you pipe your data in once, so you send your data in once. It gives you like the features, and then the softmax is the function which actually takes like this input and is trying to classify the input as one out of the 10 possible classes. And then finally what will happen is that uh, you will update, like you will find the gradients for this softmax layer, which is this linear layer, and you will update this weight, right? And then you will detach the gradient, like you will never propagate this gradient back. So in other words, like the layer 1 and layer 5 are never receiving any gradient corresponding to the label information from like the loss, but the softmax is actually receiving that information based on the classification accuracy here. Okay, so that's the whole point. And the only way like layer 1 and layer 5 and all these layers are updated is by receiving this positive data and negative data on the fly. Okay, so that's the whole point. Now there are two ways like you could train this, right? So you have like a 5 layer neural network, 5 layer network, and then you have a softmax here. So what will happen is that once you give it to softmax, it will classify 1 out of 10 possible classes, and then you compute the gradient, update the softmax, and then stop the gradient so that it doesn't propagate back. Okay, so that's the whole point. So you train like the part of the neural network with forward, and you train a part of the neural network with softmax, which uses like some sort of like backpropagation to calculate the gradients with respect to the loss. But since you are not backpropagating any gradients here, since you're like applying a stop grad, you are actually never updating the remaining layers, right? So that is still okay because you're allowed to actually update the linear layers inside the softmax, and calculate their gradients and update them, and then you can delete those gradients, right? Okay, so that's the whole point. And now how does the inference look like? So let's say that you have an image of class 7, and once you have trained this network through forward, you want to know which class it belongs to. So what you can do is like you can take this like 5 layer neural network, pass it once, and the softmax will give you the answer, right? Okay, that's good. But the problem in this whole approach is that you are still requiring a softmax to be trained. And the point is that in our brain, it is not clear that do we actually have like, so if you look at the softmax here, the last layer of the softmax will have the number of neurons which are equal to the number of possible classes. And what it is not clear whether we have like, so each of the neuron here is gonna specialize for one class. Each of the neuron here is gonna specialize for one class, and it is not clear whether we have such neurons in the brain which are actually specializing for one class separately. Okay, so there is one other way in which you can do inference in forward, and what that way is basically something which goes as follows. So let's say that what you have is just a 5 layer neural network, okay, and you just train it through forward to maximize the goodness. So you have positive sample, you have a negative sample, and you just train it through forward to maximize the activity here and to minimize the activity for negative sample. So now the key point here is that if you do that, the problem appears that uh, so if you take like your 7, so if you have image of 7, so during inference you don't know what class it belongs to. So what you can do is that you can set like out of all the 0 to 10 classes, what out of all 0 to 9 classes, what you can do is you can set each class as 1. You can set each class's pixel as 1, each class's pixel as 1, and then you can forward it through the neural network. Okay, so you can set each pixel as the 1, and then the neural network is actually trying to calculate like its activities. So let's say you took like you set 1 here, so what it means is that this is an image of digit 7, and I am appending a information of class 1 of class 0 here, that this is like a true sample. So but actually like this is not a good sample, right? So if a neural network has learned this, what will happen is that if it will look at this sample, it will actually not be able to, its activity would be very low. Okay, and similarly, so if 1 is set for all the pixels for the wrong class, its activity will be low. But if it has like, if it has if 1 is set for the class 7, then its activity will be high. So what you can do is like you have this image of digit 7, and it has 10 classes. For each of the 10 classes, you can set you can set one of the pixels as 1, and if it is like below, so out of like 9 out of those 10 classes, it will be bad, right? It will be a bad sample, and the network's activity will be low. And for one sample, for one class, it would be high, the activity will be high. So what you can do is like you can, for each of like these 10 class, for each of these 10 possible images which you can create out of this 7, the image of digit 7 and the 10 possible classes, you can calculate its the activity of the neural network. Okay, so you have an image, it can belong to any of the classes. You can set like one of the classes as 1, and you can forward it through the neural network. Okay, so you can, since you can set all of these pixels as 1, so for 10 classes you have 10 such images which you can create, and you can forward through the network. And if the network is actually outputting like a high score, so you collect like you try to calculate which of the input images has the highest score, and then that is the has the highest goodness, and that's the correct sample which your network classified. Okay, so that is how it works, and let me explain it here, where he says, okay, so after training with forward, it is possible to classify a test sample by doing a single forward pass through the net, starting from an input that consists of the test digit, and a neutral label consists of 10 entries of 0.1. So what he's saying is that you can have a 7, and then you can set all the possible values of all the possible classes as 0.1, and then your network will output like some score, will output some features which you can feed into a softmax unit to classify. Okay, so this is like what a standard softmax trained on top of a forward net will work like. But another way is, and a better way is to run the net as part of the input and accumulate the goodness of all but the first hidden layer. So what he does is that he's doing like he's processing like the network for each label separately. So if you have like an image of class 7, for each of the input classes you can set that pixel as 1, and the label with the highest accumulated goodness is chosen. So what you can do is like so if you have 10 classes, there are 10 possible labels, and you can forward pass this image, and you can collect like whichever label incurs the maximum goodness, and that will give you like the correct label. So obviously the key point here which you have to understand is that let's say that you are uh, let's say that you are using a normal softmax. So the you have like your network, and then you have your input, so the amount of time it will take you to get the answer is just one forward pass. Okay, but the other way in which he says is that if you are like taking this sample and you're setting it as all the possible, as like input with all the possible classes, what it will do is that it will take like so if it is like 10 possible classes, then here it will take like 10 possible forward passes. So you have to do 10 forward passes, right? So the number of forward passes is scaling in proportion to the number of input classes, which is like a side effect of this type of inference. But the point is that eventually you will end up, if you are doing like this sort of way, computationally intensive way, you will end up with a higher accuracy as compared to just a softmax baseline. Okay, so let me go to the let me go to the other part which he say where he has shown the results. Okay, so if you see here, so this is like comparison of a network which is trained with backpropagation and forward on CIFAR 10 with a non-convolutional network. Okay, so if you see here, what happens is that so this is like a very interesting thing. So backpropagation is the best learning algorithm which has the lowest error rate. Okay, so it has the lowest error rate, and that's actually a really good thing. Okay, it has the lowest error rate. So let's not look at this part right now. Let's only just look at the top part. So if you have CIFAR 10 and you're trying to classify, backpropagation gets a test error rate of 37%. Okay, and now when you are doing forward, okay, when you're doing forward algorithm, you have you have two ways to do it, right? One is either you run inference using a softmax, and it incurs you a error rate of 46, which is like pretty high. And another way is that you can do like 10 forward, you can do 10 forward passes for each of the 10 classes in CIFAR 10, and that will give you a error rate of 44. So now you can see that this 44 is at the expense of 10 more forward passes. And so if we write like it like this way here, okay, let me try to write it. Okay, so if you write it in here, so here this 44 is at the cost of 10 forward passes, and this is at the cost of one forward pass, and the best performance is 37. So you can imagine that this is still like these two numbers are still greater than 37, right? But for a good learning algorithm, you need like this number to be less than 37 to have a learning algorithm which is really good. Okay, so that's the point. And the forward is like able to do well on CIFAR 10, but it doesn't do well on CIFAR 100 or even ImageNet. Okay, so this is like all the algorithm which Hinton wrote about, and that is like really important. And now let me look at his experiments. Okay, okay, so he said that he took like CIFAR 10 images, and then he actually used like only two or three hidden layers. So basically all his networks are just MLP based, and they don't rely anymore on CNNs. And that is like the basic experiment he did, just to show that how a learning algorithm on MLP can behave. Okay, and his aim is not to get performance but to actually understand what is happening. So you have like these two to three layers of neural networks, and then for forward what he is doing is okay, so he trains the network in this way, and then he gets the correct answer. Okay, uh, that's the whole point. Okay, so this is it for the forward video, and as you can see, like this was a pretty cool learning algorithm, but it still has like a lot of issues in it, and I will create another video which talks about forward in more detail and actually takes care of the philosophical standpoints. So watch out for my next video. This was the basic conversation of forward, but there are a few more things happening here which I will decouple in the next video. Thank you.